Hey there, welcome to the second video on real numbers. In the previous video, we had a recap of the topics that you were taught in class 9 related to the number system. Here we'll be outlining a few of those topics briefly. So let's start off by asking a few questions. Let's ask the question, what are? The first one would be natural numbers. What are natural numbers? So natural numbers is denoted with the letter N, and they make up the set of numbers that begin with the number 1 and move forward with a difference of 1. So 1, 2, 3, 4, 5 and so on, extending to infinity. Next, we ask the question, what are whole numbers? So what are whole numbers? Whole numbers is denoted with the letter W and make up the set of numbers similar to natural numbers, except we include the number 0 here. So 1, 2, 3, 4, 5 and so on, extending to the right, denoted with the letter W. Then comes integers. So integers, in certain books they use the letter I, in certain books they use the letter Z, but I've usually come across the letter Z, and the interesting thing over here is that the letter Z comes from the German word zahlen, means to count. Alright, to count. So what are the set of numbers that make up the integers? Similar to the whole numbers, now we extend this set to the left. That is, we include all the negative numbers. So let's say, starting, of course, it extends to the left over here. So starting from a negative 4, a negative 3, a negative 2, negative 1, 0, 1, 2, 3, 4 and so on, extending to the right. Yes, so all these numbers make up the set of integers. We sometimes use the notation Z plus to call them. We introduce the letter Z with a plus to denote positive integers. I've come across these a couple of times in my higher classes as well. Yes, so natural numbers, whole numbers and integers, and if you observe these numbers, they very well fit on our number line, right? If I have the number line, I have 0 here, I have 1, 2, 3 and so on to the right, minus 1, minus 2, minus 3 and so on. So all of these numbers that we just spoke of, over here we have Z along here, so N, W and Z, all of them nicely sit on the number line. But what about these gaps, right? So I gave the spacing of a unit distance 1. So what about the gaps over here? What numbers come in between these? Of course, you can think of infinitely many numbers between 1 and 2 that I can keep on dividing and introducing decimals, etc. We'll see all of that in some time. So let's have a look at what comes in between these gaps. So the question that we ask next is, what are rational numbers? Rational numbers. Rational numbers is denoted by the capital letter Q. Q standing for the word quotient, right? And if we just focus on the word over here, rational numbers, we see another word hidden, which is ratio. So now this should give you an idea of what rational numbers are because of the word ratio. So rational numbers is nothing but a number that can be represented by a ratio of P by Q. So the caveat over here is that both P and Q belong to the integer set, that is both P and Q are basically integers, And of course, this goes without saying that the denominator of this ratio over here, the denominator over here, which is q, cannot be equal to 0. What happens if it's 0? It becomes an indeterminate form, because you cannot divide a numerator with the number 0, if it were to be 0, that is. Alright, so all these kind of combinations are rational numbers. Now this must have given you a head rush, because we have just defined rational numbers theoretically. Let's try and make things a little bit simple with an example. Alright, so let's take an example and let's choose the number 1 by 2. Right, this is a very simple number, the number half. Right, so the number half, we see 1 and 2 are both integers. My denominator is 2 over here, it's not equal to 0, so this should be a rational number. Can this be plotted on the number line? Yeah, it would definitely come between the numbers 1 and 2, right? So half, as you know by division, becomes 0.5, so sitting exactly between the numbers, oops, sorry, this is not 1 and 2, this should be 0 and 1, this should be 0 and 1, 0, 0 and 1. So exactly equidistant from 0 and 1 sits a half, correct? Anyhow, let's come back to this fraction 1 by 2. So in this fraction, we observe that the numerator and the denominator 1 and 2 cannot be simplified further if you want to represent it as a fraction, right? But there are certain numbers that simplify to 1 by 2, like say 4 by 8, yeah, or say 17 by 34, or let's get a little bit wild, say 1004 by a negative 2008. Yes, all of these simplify to 1 by 2. So are these rational or not? Obviously they are rational, but because they are not in its simplest form, we also call this as a equivalent rational. Equivalent rational. Why? Because if we were to represent this on the number line, we wouldn't have a separate position for these, right? 17 by 34. It would just be 1 by 2. So all of these are represented by 1 by 2, and these are equivalent to 1 by 2. Hence equivalent rational. Sorry, rational. All right. So this is another example of rational numbers. A few more examples maybe. Say the number 8 by 3. This is in its simplest form. Yeah. You have say negative 4 by 3, where the negative sign is associated with the numerator. You can have 4 by negative 3 or a minus of 4 by 3. So all of these are the same thing, right? Because the negative sign, whether the numerator or the denominator, does not make much difference. But of course, if you had the negative sign in both the numerator and denominator, they would simplify to a positive number. All right. So I'm just looking through a few of the basics that you guys should know. And if you didn't know, well, now you know, right? So this was about the rational numbers. So what is the next question? The next question we should ask is, what are irrational numbers? So we just saw what rational numbers were. Now we look at what are irrational numbers. Irrational numbers. Okay, so irrational numbers, your textbook very simply defines irrational numbers as numbers, NOS is denoting numbers here, guys, numbers that cannot, let me make this a little bit evident, that cannot, okay, with cannot in capital, that cannot be written in the form. What was the form? The form was P by Q. And of course, without saying, P and Q belongs to the rational, to the integer set, and Q cannot be equal to 0. Correct? So irrational numbers. So all those numbers that cannot be of this particular form of P by Q. Right? Again, this is how we define it theoretically. Let's look at a few examples. So examples, yeah, What are a few examples of irrational numbers? You all must have come across this number very often, √2. That is the positive, the square root of +2, which when we put it in a calculator or you try to do it manually, you get 1.414, and this number keeps changing, right? Going on to the right. What about √5? We all saw what √5 was, right? If you do this on your calculator, go ahead and punch in this number. You see 2.236 and goes on to the right. These are square roots of certain numbers that are pretty difficult to approximate to many decimal places, because this number is going to keep changing, right? Some special numbers that you all have already seen, say for example the representation of pi. Pi is 3.1428 and so on. So pi cannot be approximated to a very large decimal place, because this number is going to keep changing. Similarly, you all also saw the number e. You must have heard of e very lately. E is a representative of the exponential it comes from the exponential curve that you have been hearing of lately, the current coronavirus outbreak. Yes, so e approximates to 2.718 and goes on to the right. So all these numbers, the decimals that you see over here, are actually non-recurring, right? So this was about irrational numbers. We'll have a look at decimals now. We were talking about decimals, so in the next few minutes we'll be introducing concepts of the decimal. So what are decimals? What are decimals? So decimals can be of two kinds, right? You can have a terminating decimal, that is a decimal that would terminate, that would stop. Terminate means stop at some point. Terminating decimals. And you can have non-terminating decimals, right? Non-terminating decimals. Now within non-terminating decimals, you hear about two more kinds of. They are recurring. Another word for recurring would be repeating. And non-recurring decimals, non-recurring or non-repeating. I'm going to give a few examples of divisions that you could do. Say you divide 5 by 2. Over here an example would be, you say you divide 8 by 3, and over here you divide say let's just look at the value of √2, right? So when I divide 5 by 2, it comes out to be 2.5. That is, this terminates at the first decimal place as 2.5. Whereas if I divide 8 by 3, I get the number 2.6666 and going on, right? Or rather, this decimal keeps repeating itself after every decimal place. So I can also write this as 2.6 bar. So this is an example of a repeating non-terminating decimal or a non-terminating recurring decimal. What about a non-recurring decimal? So I told you, when you try to approximate √2, let's see what the value of √2 looks like. So let me bring up the calculator and let me punch in the square root of, where is the square root of? So square root of 2. So if you see this number, after every decimal place, right, 4 1 4 2 1 3 5 6 2, do you see a pattern in this, in the decimal? No, there is no pattern. So such a kind of number is approximated to about a decimal, right, and then represented on the number line. Anyway, let's just put down this value 1.414 and so on. It does not recur, it does not repeat itself. So these are also examples of irrationals, right? Irrationals. And as you would expect, your terminating number would be a rational number, because this can be expressed in the form of a fraction which was 5 by 2, right? P by Q. Same thing over here. This number could be approximated by 8 by 3, right? Anyhow, so this was about the different types of decimals. I hope this has cleared a few of your doubts that you had from your class 9. And thank you. Let's see more about even and odd numbers, prime and composite numbers in the following video. See you there.